Okay, thank you, Mr. Chairman. I would like first to acknowledge the work of my colleagues who all contributed to the work I will be presenting here. So the motivations are illustrated here. This is an ultrafine grain material that's aluminum, and it's in situ reaction in transmission electron microscope. And this was given by Marc Legault from Toulouse. So for these ultrafine grain materials, dislocation glide is limited, and so plasticity occurs by other mechanisms, and essentially you can see here by grain boundary migration. Second motivation is in this domain of geophysics. You may know that the mantle, the Earth's mantle, is mainly constituted by olivine, which is a silicate, and it's about 70% of the Earth's mantle. The problem is that olivine is an orthorhombic material with only 3 independent slip systems. So you know that according to the von Mises criterion, you need at least 5 independent slip systems to accommodate any tensor of plastic strain rate. So there is a problem because, again, you have here a material which is deprived of slip systems, and therefore dislocation glide is unable to accommodate the deformation. And there is enormous deformation over the edges because there is a convective motion of the mantle. So this is a puzzling geophysicians has been puzzling them for a number of years. So these are the motivations, and they are all related to grain boundaries and grain boundary motion. So the general purpose of this presentation is to go from atomistic to continuous description of grain boundaries, and at the same scale. So there is no scale transition here. So I've shown here, for example, the atomistic configuration of a tilt boundary, and I sketched here one slide that you will see later. That's the energy that we find from the theory, and it's superimposed on the background picture that you have here is the same as here, just to show you that the scale is the same. So you note here that the scale is 0.5 nanometers here. So there are 2 aspects in what I will say. The first one will be the description of the grain boundary structure at nanoscale. And this is mainly about elasticity, because there is no motion here of the grain boundaries. So continuity of the field variables is assumed at interatomic scale, which means that there is no discontinuity. Everything is continuous. So, and the result is that continuity removes the singularity of lattice rotation that is normally seen at grain boundaries. That is, you have one rotation on the left-hand side, another one on the right-hand side, and so at any point of the boundary, you have 2 values of the rotation. So it's ill-defined in that sense. That does not happen here because we don't have discontinuity anymore. That is, the interface is not a singular plane, it's a region with some finite widths. So the focus is on the crystal defect densities, that is here, dislocation and disclinations, rather than focusing on the atoms themselves, as for example in molecular dynamics. So that's the first part of it, and second part will be about grain boundary mediated plasticity. Then the defects that I mentioned are moving, and so a difference with molecular dynamics simulations is that we don't have to care for the atomic vibrations. We are exchanging this for dynamics of the crystal defect densities, which is obviously a dissipative dynamics. So you will see that in this way we can provide alternative mechanisms for plasticity when dislocation glides is unavailable, either in ultrafine grain materials or in materials which are deprived of slip systems. Okay, so the outline is first an elastic part, plastic one, and then conclusions. More details, but I will skip this. Okay, so the defects that we are considering here are dislocations and disclinations. So both were introduced by Volterra in 1907. The first row here is for dislocations, and this one for disclinations. So the sketch is a cylinder, hollow cylinder. The axis of the cylinder contains the axis of the line defect, either the dislocation or the disclination. And here is what happens when you cut the cylinder along a plane that terminates along the axis. So when there is a translation of one surface of the cut with respect to the other, the defect is a dislocation. So this one is a screw dislocation because the Burgers vector is aligned with the line vector of the dislocation, and these two are edge dislocations where the Burgers vector is normal to the line of the defect. So the second line here is for the disclinations. So there you have only a rotation, and again here you have what is called a wedge disclination, where the axis of the rotation is collinear with the axis, the line of the defect, and these two are called twist disclinations. Okay, so to formalize this, so first with dislocations, so I am just borrowing to Kroner here in his work of the 1950s. So a dislocation is a discontinuity of the elastic displacement or plastic displacement. In our theory, as I mentioned, there is nothing discontinuous. That is, we replace the discontinuity of the elastic displacement by the incompatibility of the elastic strain tensor, which is reflected by nice dislocation density tensor alpha. So this is what relates these two. So epsilon elastic is obviously classical notation, the elastic strain tensor. This kappa elastic is the curvature, the elastic curvature tensor. Okay, now for disclinations. So disclinations reproduce or represent the discontinuity of the elastic rotation, as shown here, and we replace that discontinuity of the elastic rotation with the incompatibility of the elastic curvature tensor. And again, this one is reflected by the width disclination density tensor theta, according to this relation here, which is due to the width in 1970. Okay, so disclinations do exist. I've seen them, and a number of these are shown here. For example, first one, you see here the scale, it's 8 nanometers. So this image has been found by, it's a Fullerene molecular layer. So fullerenes are C60, C60, C60 molecules, 1 nanometers wide. It's like a soccer ball. And you see each of them here. So in this 1 nanometer thick layer, there is only one layer of these molecules. So you see here each molecules. It's obtained through scanning tunneling microscopy. So there are disclinations that we can see from the geometry here. I'm not going to insist on this because of lack of time, but here they are, and we can see them one by one. Now these disclinations seen here are at a much larger scale. You see here 3 micrometers. This is here 2 micrometers somewhere here, and this is 4 micrometers. So in olivine, in copper, this is in recrystallized titanium with a very small strain. So all these were obtained by EBSD, so electron backscatter diffusion, and using the maps of orientation, of crystallographic orientation that we can obtain from this technique. Okay, so these disclinations and these ones are not the same one because they are not at the same scale. So we will be mainly concerned with these ones which are at this scale here. Okay, so first the elastostatic theory of dislocation and disclination fields. So all the equations, or there is an abstract or a summary of all these equations. So first the incompatibility equations that I already mentioned. So given here the alpha and theta densities, the problem is to solve for the elastic curvature and the strain, the elastic strain. For this we use the Stokes-Elmos decomposition, but I will only elaborate if you ask questions. Okay, now we use non-local elasticity at nanoscale, and so you can see that we use linear relations. That means that we are using a free energy which is only quadratic, and the only terms that are in the free energy are the elastic strain and the elastic curvature. But there are two components. One is the compatible one, and the other is the incompatible one. So when there is this orthogonal sign, that means the incompatible curvature here, and here the incompatible strain, elastic strain. Incompatible meaning here that they are related with the presence of the defect. So these are curvatures and strain which are due to the presence of the defects. So there is one point which is interesting here, and I have to stress this point. These D and B tensors, well, they are they contain a length. Due to you can have a dimensional analysis here to show this, and they are here only if there are defects. That is, if you don't have a defect, dislocation or disclination, these terms are absent. So if you have central symmetry of the crystal, you don't have this cross term here, these D and B tensors. Okay, so we need the balance of momentum and balance of moment of momentum, and we can combine them into this a higher order single equation, which is due to Minlin and Thurston in their paper of 1962. So in this equation you have only the symmetrical part of the stress tensor, which can be non-symmetric, but only the symmetrical part is here. So the skew symmetric part actually is here. And in this expression, the curl of the divergence of the coupled stress tensor, actually not exactly the coupled stress, but only the deviatory part of the coupled stress is here. The hydrostatic part disappears in the equation. So we solve this, and for example, I've shown here what we obtain for a dipole of disclinations, positive and negative, and this is the field of the normal extension in the horizontal direction. So you can notice that this is very similar to the stress field of an edge dislocation. However, if you compute also the coupled stress tensor, you can see here the components M31, so you get something which is non-zero, obviously, but which is not given by the theory of dislocations. So this is specific to the theory of disclinations. Okay, so now I'm showing here quickly how we build grain boundaries from with disclinations. So we will use periodic arrays of disclination dipole along the grain boundaries. So here is how it works. I give two examples. So this one, that's for a misorientation, which is about 36 degrees, and the second one is for 22 degrees. So take two crystals, one gray crystal and one red crystal, rotate them, so the rotation is already there. Then cut the crystals according to these broken lines here. For the gray one, this one, and for the red one, the other one, obviously. Subtract the atoms that are in the void, for example here, in this white area, and distort the material such that the broken lines will merge along the straight line of the interface. Then you get some distortion. For example, here you have a traction. You glue, of course. You take some excellent quality glue and you glue again along this interface. So what you get here is some traction, and here some compression. And this is exactly disclination also, because you have obviously a
glue 1 or glue 2?
a high quality glue. I'm sorry, I don't have a. Okay, it doesn't work anymore. Okay, so you have a discontinuity of rotation here, obviously. So these two lines are apart from each other, and you will glue them once they merge along the interface. And on the other side, there is a compression. So that means that you have a disclination dipole here. I forgot to mention that these 2 points are coincident site lattice points, and we do that for every coincident site lattice points like this. So you have an array along the grain boundary. So note that you have this polarity, red-blue, and here for 22 degrees we do the same, but we have the other polarity around. So you have a blue one and a red one here. So we define this way an arbitrary periodic array of disclinations, and the problem is that it's completely arbitrary. So what we do is we relax it. We let it relaxed in its own stress and coupled stress field until the elastic energy stabilizes. It happens that it actually stabilizes, and this is the result of the relaxed structure, which I've shown for another tilt boundary that's about 19 degrees. So again, you have here what we found from the continuous theory, and the background is the atomistic representation of the same tilt boundary. So you have here one dipole of disclinations and 2 other ones. So you can see that they fit perfectly with what is called the structural unit, atomistic structural unit, which is constitutive of the grain boundary in the atomistic representation. Okay, so this is the dilatation that we find from the continuous theory. This is just the trace of the elastic strain tensor. You can see that you have compression here and traction here, just as I mentioned, due to the building process. And this is the energy that you already show on one of my first slides. So you notice that the elastic energy is evenly distributed along the grain boundary. That it is mainly due to traction compression. There is a small amount of energy around this which is due to shear, but mainly it's due to traction compression along the dipoles. Note also again the scale, so that means that the width of the grain boundary is about 0.5 nanometers. So qualitatively, the distribution of energy are quite satisfactory, but we wanted to have a quantitative confirmation of this, so we made calculations for all misorientations and to get the elastic energy of the boundary. So our results are here in blue, and we compared with previous calculations with molecular dynamic simulations. So all ones from Hasson and others in 1972, in green here, more recent ones from CHOP and others from Georgia Tech at the time, and that's it. So you can see that we have pretty good results compared to both experimental results and molecular dynamic simulations. You need to notice also that below 10 degrees here we recover what is called the Ricciocchi energy density for low-angle tilt boundaries, which is a theory of dislocations. So we recover the classical results of the theory of dislocations. Note also that the Ricciocchi energy saturates at this level after 10 degrees. So it's completely off tracks as of the high misorientations here. We even have the cusps that are observed at these 2 angles here. Okay, so now let's talk about plasticity. So I'm first commenting about dislocation and disclination mediated plasticity. So this is I could call that the tensorial ρ1 relation. So ρ1 relation is epsilon dot is rho MBV in standard metallurgical studies. This is the same thing, except that all orientations and directions are taken here. So this is valid for any dislocation, whereas the ρ1 relation is only valid in a statistical sense. So this is valid for any dislocation. There is also a curvature plastic rate, which is due to disclinations. So when you have v theta here, that means that I am considering the velocity of disclinations. V alpha is for the velocity of dislocations. Okay, so these two quantities, the dynamics of these two quantities, alpha and theta, so the defect densities, are obtained from conservation laws for the Frankenberger's vector, which are the strengths of the defects. So it's simply a kinematic, that is you take some circuit and there is something entering and something going out, and you say that these two vectors need to be conserved, and so that's a kinematic law that gives you a framework for expressing the dynamics. For example, here there is a calculation where we show a Frank-Reed source. That's purely kinematic exercise, because we don't use we suppose that the velocity of the dislocation is constant. We don't make any relation with the stress field. So it's only kinematic exercise. It's just to show what the transport equation can do, and it can here reproduce the multiplication of a dislocation and also the annihilation, as you can see here. So we can have multiplication and annihilation. So all ingredients that are necessary to build dislocation microstructures. Okay, so there is a similar one for the disclinations, and that's obtained from the conservation of the Frank vectors. So this is kinematics. Now this is for actual dynamics. So we do, of course, some thermodynamics. So we write the dissipation as a function of the plastic strain rate. So that's due to a dislocation motion, and also with the curvature plastic curvature rate, and this reproduces the motion of disclinations. So the dual terms are the symmetric part of the stress tensor and the deviatoric part of the coupled stress tensor. So using this, I can show here, I can extract the velocity of dislocations and disclinations, and the conjugate factor would be the driving force. So this F alpha will be and is actually the traditional pitch color force that you can recognize here, for example, but it can be also expressed as a function of the stress tensor. And I can define another driving force for disclinations from the conjugate term of the velocity here. And you see that this driving force actually uses not the stress tensor, but the coupled stress tensor, and actually the deviatoric part of the coupled stress tensor. Now I have to give a constitutive law, or at least a framework for constitutive law, because this dissipation has to be positive. So the simplest way is to use some drag, viscous drag, in this manner. So this pitch color force is proportional to the velocity of dislocation, and this B alpha, which is a mobility, has to be positive. And same thing for the disclinations. So here is if you want to elaborate about the physics, this is where you have to go. That is, if it's only viscous behavior, you take it as a constant. If you want to have some thermally activated mechanism for obstacle overcoming, that will go into this one. So here we want to do very simple things. Thank you. So we take only a constant. Okay, so here are the results regarding shear-coupled boundary migration. So we apply here a shear stress, and we start with the array of disclinations here, And what you can see is that, that's it for data in copper, what you can see is that this array is moving downward in that case. So the mechanism is as follows. So the applied shear strain induces coupled stresses in the defect area due to this B and D tensor that I mentioned. And therefore, since you have coupled stresses, you can drive motion, disclination motion. So they are driven this way in that case. So the exact mechanism is as follows here. It's shown here. So you have a dipole of disclinations, and they are moving here downward. So in the process, while they are moving, they generate dislocations. Actually, only partial dislocations because the vector Burgers is very small, and this dipole of dislocations actually annihilates. And in the process of annihilating, they produce the shear. So you have shear which is produced in the area that is swept by the boundary. So, okay, so you can also notice that it's perfectly inhomogeneous. That is, you have here a distribution of plastic rotation and plastic strain, and you can see that it's evenly distributed along the grain boundary. So the migration that we obtain for copper is of the order of 0.1 micrometers per second, which is very much consistent with experimental data. Okay, so we did that for all misorientations, and we plotted here the shear coupling factor, which is a slip over the migration. So there are two distances, and this is what happens for small misorientation angles up to 38 degrees. There is a motion up like this one for 22 degrees, and they are aligned. It's a straight segment, and there is a branching here with an abrupt change to another branch with negative motion, as in this one. And again, we recover exactly the experimental data along these two straight lines here. Okay, so another example, that's for olivine. So olivine is much more difficult than copper because copper is FCC and that's classical. This is orthorhombic structure, and actually we had to use the disclination quadruples and not dipoles to reproduce the structure of the grain boundary, but we managed to do it. So here is, for example, the energy that we get from this representation, and this is the motion that we get for olivine. So again, but we have here only one misorientation. So the fact is that the shear-coupled migration provides an additional deformation mechanism for olivine, and that's something that the geophysicists were longing for. Okay, conclusions. First, this theory is able to provide a detailed description of the grain boundary structure that is results in elastostatics, and also in grain boundary migration, that is even plasticity can be reproduced. We can have the results in a quantitative way, and we can see here, due to these results, that continuity is actually relevant for the description of the core properties of the defects in the boundary. So incompatible elasticity is absolutely key to this description. It is these B and D tensors which express non-local properties. They are essential. If they are not there, we cannot obtain boundary migration. So boundary migration is due to the non-local aspects of elasticity. Third point, I want to stress this one. So the characteristic length scale is 0.5 angstrom, which is very small, but you cannot see here, but there is a reference by a paper by Maran-Ganti and Sharma in the JMPS 2007, where they obtained this length scale from DFT ab initio calculations. So we just borrowed these results. They perfectly fit with what we do because they effectively restrict the non-locality to the grain boundary itself. Okay, so what we did here is this that I've shown here. So you can recognize that sketch. This is the size of the sample, the time scale of the experiment. So when you do ab initio calculations, molecular dynamics, crystal plasticity, you are around here. What we do is this, with this theory, is something like that. That is, we can cover both this scale in the nanometers and also in the millimeters, let's say. But what I've shown here is there is no scale transition. That is, I stick with that scale here, but we do have time course graining. That is, as I mentioned, you do not have to resolve the atomic vibrations. So you can call that time course graining. Spatial course graining will be the next step of the analysis. And thank you very much for your attention.